All right, section 5 of the circle unit is going to talk about some of the tangent line properties. And if we just take a minute to review what a tangent line is, remember it is a line which touches the circle at exactly one spot. And they can be wherever you would like on that circle, they just touch one time. So the perpendicular tangent theorem says, in a plane, a line is tangent to a circle if and only if it is perpendicular to the radius. And this is a hugely important theorem. Now, because this is an if and only if, we can work it both ways. If I have a radius and it's perpendicular, I know the line is tangent. If there's a tangent line and it touches a radius, it has to be perpendicular. The reason this is so crucially important is then I can draw on a right triangle. And once I have a right triangle, I can use the Pythagorean theorem. I can use triangle angle sum. I have a lot of power to solve and find different pieces of the segments in that circle. Another really powerful theorem is the congruent tangents theorem. If two segments are drawn from the same exterior point, like C, and are tangent to the same circle, like CA is tangent here, and CB is tangent here, then those two pieces are congruent, and you see that marked. If you want to think about, though, this is really a kite, because what forms these are radii, which are congruent, and now I have two pair consecutive congruent sides, which is the definition of the kite. So now all of my properties of kites apply. Previous theorem, I have 90 degrees in those corners. That makes the opposite angles equal. I have the congruent I have all of those really cool things about kites from the previous unit. So if we put this into practice and look at some examples, our first one is here. And it says find AC. AC is this whole length. Now AD is clearly 5 because that's also a radius. But I want the whole length. So what I want to see is the fact that this is a triangle. More importantly, here is a radius with a tangent line, so that is a right triangle where this is my hypotenuse, and once I have a right triangle, I can write c squared is equal to 5 squared plus 8 squared, and I can solve for that missing side. So this means that c squared is equal to 25 plus 64, and so c squared is equal to 89. Take the square root of both sides. C is equal to the square root of 89, or approximately 9.4. If we go ahead and look at the next example and find the perimeter of the quadrilateral. This is the congruent tangents theorem in action. This tangent point to this point to this point are congruent, so this piece is 8. From this tangent point back here and here, those two are congruent, so this piece is 4. From point G, tangent back at H, tangent back at F, those are congruent. Now, right now, I don't happen to know how big those are because this entire side is 6. There may or may not be a bisector. So if I keep moving, from E, tangent back to D is 3, tangent back to F, that means those are equal. That's 3. If the whole thing is 6, that makes this one 3, makes this one 3. Now, to find perimeter, I take a walk around the outside of my figure, and I end up adding 4 plus 8, which is 12, plus 3 plus 8, which is 11, plus 6 on this side, plus an additional 7, and this whole thing ends up being 36 units. Now be careful that you're keeping your tangents so they're not equal all the way around, but you just have equal tangent segments at each of those exterior points. Go ahead and try the quiz questions that follow and tune in for part 2 of the video.